All right, so this is going to be our homework walkthrough for the assignment titled Limits and Continuity Extra Review. So this is just one of the assignments. It's a review for our midterm, right, for our first semester midterm here. We're just gonna do a whole bunch of limits to begin with, and then we will do some continuity problems and stuff like that towards the end. So our first one here is the limit as x approaches infinity of e to the 7x over 7x to the fifth. Well, both of those are infinity, but an exponential function is going to increase faster than a polynomial function. Therefore, the numerator is going towards infinity faster, which means the limit here is just infinity. Remembering that exponential functions are the fastest to infinity that we will deal with, followed then by polynomial functions, then root functions, and then logarithmic functions. Right, so in that order, at least of the functions that we deal with for this class, that's the fastest to the slowest. Right, so fast to slow. So our next one here is another one that ends up being infinity over infinity, right? The natural log of infinity is infinity, and as x goes to infinity, x is infinity. But the polynomial function, that linear one, is going to increase more quickly than the natural log function does, and therefore the denominator is going to infinity faster, which means this is trending towards 0. Same idea here. X cubed goes towards infinity. 2 to the x goes towards infinity. But 2 to the x is exponential, which means it's going to infinity faster, which means that this limit tends towards 0. And we've got one more of these. So this one, we've got infinity for our root x and infinity for our x cubed. But x cubed is increasing much more quickly than root x is, and therefore this tends towards 0 as well. For our next one here, we have a limit as x approaches infinity of root x squared plus 1 over 3x minus 5. And so this is one of the functions that it does equal infinity over infinity, but because the effective degree here is kind of the same, right? It's root x squared, which the degree of that is sort of like a 1, right? Root x squared is like x sometimes. And 3x is also a power of 1. We can't just use that same thing to see which one's going towards infinity faster. And in fact, we might try to use L'Hopital's rule, something we talked about during the applications of the derivative unit, but this is one of the ones that goes into an infinite loop with L'Hopital's rule. So we have to remember that the appropriate way to solve limits like this is to just divide inside of the square root by x squared, which means that in the denominator, we also have to divide by the square root of x squared. Now, dividing by the square root of x squared means that we have to think about what that is. Well, the square root of x squared isn't just x, it's actually the absolute value of x. Because when x is positive, right, we just get x, but when x is negative, we actually get the positive version of x. And then we have to remember that if x is greater than or equal to 0, the absolute value of x, I don't know why I wrote a 0 there, is equal to x. So we have absolute value of x here, but because x is approaching infinity, x is greater than or equal to 0, the absolute value of x is just x. So this becomes a limit as x approaches infinity of the square root of, well, I can simplify the numerator there, 1 plus 1 over x squared, over 3x minus 5 over x, which can then be rewritten as a limit as x approaches infinity of square root of 1 plus 1 over x squared over 3 minus 5 over x. And from there, we should be able to evaluate that at infinity. So what we'll do is we'll just plug in infinity, noting that as x goes to infinity, 1 over x squared is 0, and 5 over x is also 0, right? That's 1 over infinity and 5 over infinity. Both are 0. So this becomes a limit as x approaches infinity of the square root of 1 over 3, which is just 1/3. Now for our next one here, this is of course the exact same function, but this time we're doing the limit as x approaches negative infinity. So when we go about solving this one, we're going to use the exact same process to start, where we divide by an x squared inside the square root. But this time, as we said, the square root of x squared is equal to the absolute value of x. And the absolute value of x in the last problem we turned into x, because x was greater than or equal to 0. But now x is approaching negative infinity, which means x is less than 0. Well, if x is less than 0, then the absolute value of x is the opposite of x. So we'll rewrite this similarly to how we did with the previous problem. Right? It'll be the square root of 1 plus 1 over x squared in the numerator, but in the denominator, it'll now be 3x minus 5 over the opposite of x. And so that will allow us to rewrite this as a square root of 1 plus 1 over x squared over negative 3 plus 5 over x. And as x goes to negative infinity, this just becomes the square root of 1 over negative 3, which is negative 1/3. So a key difference here on this problem with the last one, right? We end up with a negative 3 in the denominator instead of a positive 3 in the denominator. This is another one similar to the last one, so we're going to just go through and use the exact same steps here, right? So this is the limit as x approaches infinity of, well, in the denominator, we're going to divide by x squared inside that square root, which means that I'm going to divide by x squared inside of a square root in the numerator. And again, because we know, just like in the last couple problems, the square root of x squared is the absolute value of x, and as x goes towards infinity, x is greater than 0, so the absolute value of x equals x. So this will turn into a limit as x approaches infinity of 5x plus 1 over x, all over the square root of 16 minus 2 over x squared. Now we can evaluate, we should do the numerator simplification first. 5x over x is 5 plus 1 over x, all over the square root of 16 minus 2 over x squared. As x goes towards infinity, both 1 over x and 2 over x squared go towards 0. So we end up with 5 over the square root of 16, or 5 over 4. And for this one, it's essentially the same thing. We're going to do 5x plus 1 over the square root of x squared divided by that square root of 16x squared minus 2 over x squared. And of course, as we said before, the square root of x squared is the absolute value of x, but this time x is less than 0, which means that the absolute value of x is the opposite of x. So this becomes a limit as x approaches negative infinity of 5x plus 1 over negative x, all over the square root of 16 minus 2 over x squared. So now we can do the division in the numerator, giving us the limit as x approaches negative infinity of negative 5 minus 1 over x, still over the square root of 16 minus 2 over x squared. And the 1 over x goes to 0, just like the 2 over x squared goes to 0, and we're left with negative 5 over the square root of 16, which is 4. So we get negative 5/4. For our next one here, we've got the limit as x approaches 3 of x squared minus 9 over x squared minus 7x plus 12. So if we try to plug in 3, as we should with all limits, we get 0 in the numerator, and we get 9 minus 21, which is negative 12, plus 12, which is 0. So we get 0 over 0, which means now we have to kind of make a decision as to how we want to go about evaluating this limit. So one option is to just factor, right? So we can say this is equal to the limit as x approaches 3 of x plus 3 times x minus 3 over x minus 4 times x minus 3. And we can see then that because x is approaching 3 and not equal to 3, we can cancel out those x minus 3's, giving us a limit as x approaches 3 of x plus 3 over x minus 4, which is 6 over negative 1, or negative 6. The other option is to use L'Hopital's rule. And when we use L'Hopital's rule, the College Board wants you to write out the separate limits of the numerator as 0 and the denominator as 0. And then say that you're using L'Hopital's rule. And just take the derivative of the top, which is 2x, and the derivative of the bottom, which is 2x minus 7. Plug in the 3, you get 6 over negative 1, which is negative 6. So you can choose to do this problem whichever way you want to. So either show the factoring and the canceling, or show that the separate limits are 0 and use L'Hopital's rule. It doesn't really matter which option you choose. For this next one, we've got the limit as x approaches negative 3 of x squared minus 9 over x squared minus 7x plus 12. So this is one where I would caution you, don't just look at something that looks like it should factor and cancel some things out and assume it's 0 over 0. Right? Always actually test to make sure it's 0 over 0. Plug in that number before you do anything else. So negative 3 squared is 9, and 9 minus 9 is 0. In the denominator, we get 9 plus 21 plus 12. Well, 9 plus 21 plus 12 is certainly not 0, right? I mean, that's 42. So 0 divided by 42 is just going to be 0. And if you try to go right to using L'Hopital's rule here, you're going to get a very wrong answer to this problem. Right? So don't use L'Hopital's rule unless you are confirming that it's 0 over 0 or infinity over infinity. All right, for our next one here, if we plug in negative 5 to this, right, we get negative 125, and then plus 25 times 7, so that'd be plus 175, minus 50. And in the denominator, we get 25 plus 10 minus 35, which is 0 over 0. So you have two options. One is to factor, or the other is to use L'Hopital's rule. And it doesn't really matter, again, which one you use. If you're going to use L'Hopital's rule, which I guess was what we'll do here, make sure that you show that each separate limit is equal to 0, because that's what the College Board wants to see. State that you're using the rule, and then just use it. Right? It's now a limit as x approaches negative 5 of the derivative of that numerator, which is 3x squared plus 14x plus 10, all divided by the derivative of the denominator, which is 2x minus 2. Now just plug in the values that you have here. So if we plug this in, if we plug in negative 5, we're going to get 75. And then looks like that's minus 70 plus 10 in the numerator. And in the denominator, it's going to be negative 10 minus 2. So we end up with, looks like that's 75 minus 70 is 5. Right, plus 10 should be 15. So we have 15 over negative 12. Divide those both by 3, and you get negative 5 over 4. All right, for our next one here, we have a limit as x approaches negative 4 of x squared minus 3x minus 4 over x squared minus 4x. So just go ahead and plug in the negative 4 first, right? So we end up with 16 plus 12 minus 4 over negative 4 squared is 16, and then minus 4 times negative 4, so plus 16 more. So really what we've got here is 16 and 12 is 28, minus 4 is 24 over 32. Those both divide by, they both divide by 4, right? Or they both divide by 8. All right, so that should be 3 over 4. All right, for our next one here, we've got the same function, x squared minus 3x minus 4 over x squared minus 4x, but this time we're evaluating it as x approaches 4. So that's going to be 16 minus 12 minus 4 over 16 minus 16, which is 0 over 0. So you can use L'Hopital's rule, or you can factor. I think this time we'll just do this one with factoring this time. So this becomes a limit as x approaches 4 of x minus 4 times x plus 1 over x times x minus 4, right? If you just factor the x out of that. So we're just left with the x minus 4's canceling, giving us a limit as x approaches 4 of x plus 1 over x. Well, if we plug in 4 to that, we get 5 over 4. For our next one here, we have x squared plus 36 over x squared minus 8x plus 12 as x approaches 6. So plug in 6 and you get 36 plus 36, so not indeterminate for sure, over 36 minus 48 plus 12. Well, that's 72 over 0. Well, we can't do 72 divided by 0. This doesn't exist, so the limit does not exist. For our next one here, we have a limit as x approaches 0 of sine squared x over 3x squared. So the first thing we'll do here is check what happens if we plug in 0, but we clearly get 0 over 0. We could use L'Hopital's rule here. If we use L'Hopital's rule, we might notice that we're going to get 6x here, which will still be 0 in the denominator. So if the numerator is still 0, we'd have to take a second derivative here. We have to do L'Hopital's rule twice. So I think if you have to do L'Hopital's rule more than once with the kind of basic trig functions, I would suggest just doing what we did in the first unit, which is pulling the constant of that 1/3 out. Then you can rewrite it as just sine of x over x being squared. So really all we end up with here is just 1/3 of the limit as x approaches 0 of sine of x over x, because once the whole fraction is being raised to the second power, you can pull it outside the whole limit. And we just get 1/3 of 1 squared, because we know that the limit as x approaches 0 of sine x over x is 1. Well, 1/3 times 1 squared is just 1/3. For this one, we definitely don't want to try and use L'Hopital's rule, because 3x to the 10th is going to require a lot of derivatives to get it down to be not 0 when we evaluated at 0. So we'll pull out the 1/3 just like we did in the last one. We'll have 1/3 the limit as x approaches 0 of sine of 4x squared, which is being raised to the 5th power, over x to the 10th. Well, x to the 10th is x squared to the 5th power. So I could rewrite this as sine of 4x squared over x squared all to the 5th power. And then I know that if I get a 4x squared in my denominator, then that limit inside would be 1. Well, I can't just put a 4 there without putting a 4 in the numerator as well. So I'll put a 4 in the numerator as well. And then we'll pull that 4 outside of the limit, because it's just a constant. But as we do that, we have to be careful that that 4 is inside of a parenthesis that's being raised to the 5th power. So as it comes out, it becomes 4 to the 5th power over 3, now times a limit as x approaches 0 of the sine of 4x squared over 4x squared, all raised to the 5th power. And 4 to the 5th power is just 1024. So we have 1024 over 3 times now 1 to the 5th, which will be 1024 over 3. Our next one here is the limit as x approaches 0 of x cubed minus 5 sine 2x over 3x. And we'll note that if I look at the limit as x approaches 0 of the numerator, I get 0 minus 0, which is just 0. And if I look at the limit as x approaches 0 of 3x, I get 0. So this is a good candidate for using L'Hopital's rule. It's not the only way that we could do this problem. We could split it into two different limits. But I think at this point, now that we know how to do derivatives, it might be quicker and easier to just use L'Hopital's rule. The derivative of x cubed is 3x squared. And using the chain rule, the derivative of 5 sine 2x should be a 10 cosine 2x. So, and we have the negative in front of it already. And so then we will just divide that by 3. Now we can evaluate this when x is 0. 3x squared would be 0. Minus 10 cosine 0 all over 3. Well, the cosine of 0 is 1. So this is negative 10 over 3. Here's another one that we have a couple of options for. And this is 1 minus cosine 7x over 4x. So I'm going to show this one two different ways. We might note that the limit as x approaches 0 of 1 minus cosine 7x is equal to 0, right? Because it's 1 minus the cosine of 0. And also that the limit as x approaches 0 of 4x would be equal to 0. And so using L'Hopital's rule, we could say that this is the same as the limit as x approaches 0. Well, the derivative of 1 is 0. And the derivative of negative cosine of 7x, using the chain rule, should be 7 times the sine of 7x, all over 4. And if we plug 0 into that, we get 7 times the sine of 0 over 4. Well, the sine of 0 is 0, so that's just 0. Our other option would have been to pull the 1/4 out, so that we have 1 minus cosine of 7x over x. And knowing that during the first unit we proved and then memorized some rules for limits that 1 minus cosine x over x as x approaches 0 is equal to 0, we could then just try to get a 7x in the denominator, which would mean that I'd have to multiply the top by 7, and then pull that 7 out to the front, giving us 7/4 of the limit as x approaches 0 of 1 minus cosine 7x over 7x. Well, since we know that the limit as x approaches 0 of 1 minus cosine 7x over 7x is 0, we just have 7/4 times 0, which is 0. So either way is fine. For our next one here, we had a rule that the limit as x approached 0 of tangent x over x was equal to 1. So we could go ahead and use that rule, or we could use L'Hopital's rule because it's 0 over 0. It doesn't really matter which option you choose. I guess for this one, let's do L'Hopital's rule this time. So the limit as x approaches 0 of the tangent of 12x is 0. And the limit as x approaches 0 of 5x is equal to 0. So using L'Hopital's rule, we can say that this is the same as the limit as x approaches 0 of the derivative of tangent 12x, which should be 12 secant squared 12x, all over the derivative of 5x, which is just 5. And we'll plug in 0, so we have 12 times the secant squared of 0 over 5. Well, the secant of 0 is just 1, so we end up with 12 times 1 over 5, which is 12 bits. All right, for our next one here, this one is definitely a problem that we do not want to try and use L'Hopital's rule on, even though it's 0 over 0. And we can see that it's 0 over 0. What we'll do is we'll use our limit rules from the first unit. We'll pull out the 1/5, right, from the 5 from the denominator. And we can rewrite it as the tangent of 3x squared over x squared, all being raised to the 4th power, right? Because that gives us the x to the 8 in the denominator, and it gives us the tangent to the 4th of 3x squared. So we'll throw a 3 into the denominator and a 3 into the numerator, and then pull that 3 from the numerator out, remembering that it is a 3 to the 4th power. So we'll have 3 to the 4th over 5. And now everything inside of that limit is being raised to the power of 4. So we can pull that power of 4 outside the entire limit. And because we proved that the limit as x approaches 0 of tangent x over x was equal to 1 during the first unit, we can use that property now and just say that we've got 3 to the 4th, which is 81, over 5, times 1 to the 4th power, which is, of course, just 81 over 5. For our next one here, we've again got 0 over 0. So we have two different ways to go about this one. I think we'll just go right ahead and use L'Hopital's rule here. So we can show that the limit as x approaches 0 of the sine of 8x is 0. And also that the limit as x approaches 0 of the sine of 3x is equal to 0. So we can then just rewrite this using L'Hopital's rule and take the derivative of both the top and the bottom. So this becomes a limit as x approaches 0 of the derivative of sine 8x, which according to the chain rule is 8 cosine 8x, and the derivative of sine 3x, which is just 3 cosine 3x. So plug in 0 and you get 8 cosine 0 over 3 cosine 0. And, well, cosine of 0 is just 1, so we get 8/3. For our next one here, we've got a limit as x approaches 0 of the tangent to the 5th of 2x over the sine to the 5th of 2x. Well, everything inside this limit is being raised to the 5th power. So I'm going to just pull that 5th power outside of everything. And now all I have to do is worry about evaluating that limit that's on the inside here. And so we know that the limit as x approaches 0 of tangent 2x is 0. And also that the limit as x approaches 0 of sine 3x is equal to 0. Therefore, we can use L'Hopital's rule and say that this should be equal to the limit as x approaches 0 of the derivative of tangent 2x, which is 2 secant squared 2x, divided by the derivative of sine 3x, which is 3 cosine 3x. And of course, it's all still raised to the power of 5. Well, that gives us 2 times the secant squared of 0 over 3 times the cosine of 0, all to the 5th power. And we know that the secant of 0 and the cosine of 0 are both 1. So 2/3 to the 5th power should be 32 over 3 to the 5th, which is 243. All right, for our next one here, we've got a limit as x approaches 0 of a whole mess of a function up here. So first thing we should, of course, do is just plug in 0 and see what we get. So 3x would be 0. The sine of 0 would be 0. The cosine of 0 would be 1, so we have minus 1 plus 1. And in the denominator, we'll have 0 plus 1 minus the cosine of 0, which is 1. So it looks like that's 0 over 0, which means this is a good candidate for using L'Hopital's rule. So we'll state that the limit as x approaches 0 of the numerator is 0. And also that the limit as x approaches 0 of the denominator is equal to 0. And then we'll use L'Hopital's rule. So L'Hopital's rule will say that this is equal to the limit as x approaches 0 of the derivative of 3x is 3. The derivative of sine 2x is 2 cosine 2x. The derivative of negative cosine x should be positive sine x. And the derivative of 1 should be 0. And in the denominator, the derivative of x is 1. The derivative of 1 is, of course, 0. And the derivative of negative cosine x should be a positive sine of x. So now we'll just evaluate this at 0 and see what we get. We get 3 plus 2 cosine 0 plus sine 0 over 1 plus the sine of 0. Well, cosine of 0 is 1, so that's 3 plus 2, which is 5. And the sine of 0 is 0, so that's gone. And it's over 1 plus the sine of 0. The sine of 0 is 0, so that's just 1 plus 0, 1. So we just get 5. All right, for our next one here, we're looking at the limit as x approaches 3 from the left of the absolute value of x minus 3 over x minus 3. So in order to evaluate this, we have to clear that absolute value off of the numerator, which means we have to look at what our limit is doing. X is approaching 3 from the left, which means that x is less than 3. Well, that means that the thing inside the absolute value, which is x minus 3, is less than 0. And the definition of absolute value says the absolute value of something, we'll call it u, is equal to u if u is greater than or equal to 0, and the absolute value of u is equal to the opposite of u if u is less than 0. Well, our u, x minus 3, is less than 0. So this should become a limit as x approaches 3 from the left of, we can clear the absolute value by taking the opposite of what's inside of it. So opposite of x minus 3 over x minus 3. The x minus 3's will cancel, leaving us with a limit as x approaches 3 from the left of -1. And of course, the limit of a constant is just the constant. We're going to use the same basic idea here for this one. So this time we're approaching -4 from the right. So if I'm approaching -4 from the right, that means that x is going to be more than -4, or that x plus 4 is going to be more than 0, which means that the absolute value of x plus 4 should just be x plus 4, which means I can now cancel those out and just turn this into a limit as x approaches -4 from the right of 1. Well, the limit of a constant is the constant, so our answer is just 1. And we'll do another similar thing here. We're approaching 2 from the right, which means that x is greater than 2. And if x is greater than 2, then x minus 2 is greater than 0. So the absolute value of x minus 2 is going to just be x minus 2. So this becomes a limit as x approaches 2 from the right of 2 minus x over x minus 2. Well, those aren't set up to cancel yet. What we need to do is we need to factor a negative out of either the top or the bottom. I'll just factor it out of the top, leaving me with the opposite of x minus 2 over x minus 2. Now I can cancel the x minus 2's and get a limit as x approaches 2 from the right of -1. The limit of a constant is the constant, so we just get -1. All right, our next one here is a limit as x approaches 2 of this nice little complex fraction that we've got here. So the first thing we should do is we should check and see what we get if we actually plug in 2 to this fraction. So if we do that, we end up with 4/5 minus 4/5 over 2 minus 2, which is clearly 0 over 0. So we need to either use L'Hopital's rule or just simplify the complex fraction. I don't think L'Hopital's rule is a great option here, just because those are kind of annoying derivatives. It'll work. You're welcome to use it if you want. But I think I normally prefer to just get a common denominator. So the limit as x approaches 2 of, well, let's see, we have 4 over x squared plus 1. And we need to give that a denominator of x squared plus 1 times x plus 3. So we'll multiply by x plus 3 over x plus 3. And then we'll have -4, and that one had an x plus 3, but it needs to have an x squared plus 1 also, so we'll multiply by x squared plus 1. And in the denominator, we still just have 2 minus x. Now we can combine those fractions together And we'll end up with 4x plus 3, or 4 times x plus 3, which is 4x plus 12. Make sure you don't forget, like I almost did, to write your limit as x approaches 2. So a limit as x approaches 2 of 4x plus 12 minus, make sure that minus sign gets distributed to everything. So minus 4x squared minus 4. And then that's all over the x squared plus 1 and the x plus 3, but also it's all over 2 minus x as well, right? I can put that 2 minus x from my original denominator over 1, and then it's like a fraction, the big fraction in the numerator, divided by the smaller fraction in the denominator. I can just multiply by the reciprocal, which means I'm multiplying the top by 1, which does nothing, and the bottom by 2 minus x. So now we no longer have a complex fraction here, and we can combine our terms together in the numerator, right? So that's going to give us a limit as x approaches 2 of, and we've got here a negative 4x squared, and then we've got a plus 4x and a plus 8, and it's all over x squared plus 1, x plus 3, and 2 minus x. And if we want to factor that down, I think we can see that the right step here is probably going to be to take a 4, and we could take a negative 4 out of it. But I'm just going to take a 4 out of this. So if I take a 4 out of the numerator here, it's going to look like 4 times negative x squared plus x plus 2. Right? So I'm going to have a 4, and then that'll factor into a negative x and an x, hopefully, up here. And so we'll do that in a second. We're going to have an x squared plus 1 and x plus 3 and a 2 minus x down here in the denominator. And so we need to get an 8 as our last term. And so in order to get an 8 as our last term, or sorry, not an 8, a 2 as our last term, we're going to have to multiply by a 1 and a 2, right? Because we've already factored out the 4 here. So we're gonna need a 1 times a 2, and then we need to end up with a positive 1x here in the middle, which means that I don't want to multiply the 2 by the negative x. I want to put the 2 there and the 1 here, so that I now have, a negative x squared, a negative x, and a positive 2x, which gives me a positive 2x, and a positive 2. And the nice thing about this is that we can see that the negative x plus 2 should cancel with the 2 minus x. Those are the same things, just with the terms reversed. And so now, we're kind of low on room here. Try and fit this all on the page here. Limit as x approaches 2 of 4 times x plus 1 over x squared plus 1 times x plus 3. We can just plug in 2 now, which gives us a 12 in the numerator, 4 times 3. And in the denominator, it gives us a 5 times a 5, which would be 25. So we end up with 12 over 25. For our next one here, I think maybe we'll try and just see if we can do this one using L'Hopital's rule. If we look at the limit as x approaches 3 of 2 over x squared plus 1 minus 1 over x plus 2, we can see that that is 2/10 minus 1/5, which is most definitely just 0. And if we do a limit as x approaches 3 of x minus 3, that is definitely 0. So just to show that we can do these complex fraction ones using L'Hopital's rule also, we'll do one. So this becomes a limit as x approaches 3 of the derivative of 2 over x squared plus 1. And that's just a constant over a function. So we had a rule for that. It's called the reciprocal rule. It equals the opposite of the derivative of the denominator times that constant. So we had the constant of 2. The derivative of the denominator was 2x. And then we also have an x squared plus 1 squared in the denominator there. And the same goes for the minus 1 over x plus 2. So we have the minus in front, But since we're doing the reciprocal rule, we end up with another minus sign in front of that. So plus the derivative of x plus 2, which is 1, all over x plus 2 squared. And then it's all over the derivative of x minus 3, which is just 1. And so maybe this is just a little bit easier. I don't know. We'll just evaluate this when x is equal to 3. So we end up with negative 2 times 3, which should be negative 12, over 3 squared is 9, plus 1 is 10. 10 squared is 100. So we have negative 12 over 100, plus 1 over, and then we have 3 plus 2, which is 5, squared is 25. So if we get a common denominator here, that's going to be 100, right? So we'll just multiply by 4 over 4. Negative 12 plus 4 is negative 8 over 100. We can, of course, divide those both by 4 to get negative 2 over 25. Or you could have just reduced the negative 12 over 100 right into negative 3/25 and then added that way. So it still works using L'Hopital's rule. So for these complex fraction ones, just do whatever you feel is easier for you. Either use L'Hopital's rule or get the common denominator. I guess we'll do this one. We'll try and do this one using the common denominator method. Then we'll try the next one maybe again with L'Hopital's rule. So we can see that if we plug in 3 to this, we get 4/6 minus 2/3, which is 0, and then over 3 minus 3. So it's definitely an indeterminate limit. So we're going to get our common denominator. We're going to do a limit as x approaches 3 of 4 over x squared minus 3. And we're going to multiply by x and by x here. And then minus 2 over x. And we're going to multiply by x squared minus 3 and x squared minus 3. And just like before, it's all over the x minus 3 over 1. This time I'll write the over 1 so that we can recognize that we're going to get rid of that and multiply by the reciprocal. So we have a limit as x approaches 3 of 4x minus 2x squared, and then plus 6, all over x times x squared minus 3 times x minus 3. And now we will simplify out that numerator. This time, I think we will take out the negative from the whole thing. So it's a limit as x approaches 3. And we're going to take out a negative 2 in the numerator, leaving us with a positive x squared. And then if we take a negative 2 out of positive 4x, that'll be minus 2x. And a negative 2 out of positive 6 will be minus 3. All over x times x squared minus 3 times x minus 3. Now we need to factor out that numerator. So we have a limit as x approaches 3 of negative 2. And then the factorization of x squared minus 2x minus 3, it should be 2 x's, of course, right? X and x there. And we need a minus 3 and a positive 1. And it'll all be over x times x squared minus 3 times x minus 3, allowing us to cancel out the x minus 3's, giving us a limit as x approaches 3 of negative 2 times x plus 1 over x times x squared minus 3. And now we should just be able to plug this in. We have negative 2 times 4, which is negative 8, over 3 times 9 minus 3, so 3 times 6, which should be 18. Well, negative 8 over 18 should be both divisible by 2, so negative 4 over 9. All right, we've got another one that we'll confirm that it's 0 over 0 and see if we can use L'Hopital's rule this time. So that gives us 4/8 minus 2/4 in the numerator over 10 minus 10. So yeah, 4/8 and 2/4 are both a half, so right? That's 0 over 0. So we'll go ahead and use L'Hopital's rule, which I think maybe is algebraically quite a bit simpler. We'll just do L'Hopital's rule. So we have a limit as x approaches 5 of the derivative of 4 over x plus 3, which using the reciprocal rule is the opposite of the constant times the derivative of x plus 3, which is 1, over x plus 3 squared. And then minus the opposite of, so we'll make that a plus, our constant times the derivative of x minus 1 over x minus 1 squared. And then this time it's over the derivative of 2x minus 10, which is 2. So now we'll just evaluate. And as we do that, we could choose to simplify a little bit here if we wanted to, right? This 4 and this 2 are both divisible by 2. So we could do that if we want to, but if that's going to, I feel like that might mess some people up algebraically, so I think maybe we'll just leave it. We'll do negative 4 over 5 plus 3 is 8, so 8 squared is 64. And then plus 2 over 5 minus 1 is 4, 4 squared is 16, all divided by 2. And so negative 4 over 64, that should reduce to negative 1 over 16. So we have negative 1 over 16 plus 2 over 16, all divided by 2, which will be 1/16 divided by 2, which will be 1 over 32. And we've got one more here. I guess I don't see why not. Let's just use L'Hopital's rule again. That seems like it's going a little more quickly for us. So we'll do a limit as x approaches 3 of 3 over x squared plus 3 minus 1 over x plus 1. Well, that's 3 over 12 minus 1 over 4, which is clearly 0. And the limit as x approaches 3 of x minus 3 is also clearly 0. So we'll use L'Hopital's rule, giving us a limit as x approaches 3 of the derivative of 3 over x squared plus 3, which will be the opposite of the constant times the derivative of x squared plus 3 over x squared plus 3 squared. And then minus the opposite of that constant, 1, times the derivative of x plus 1, all over x plus 1 squared. And then it's all divided by the derivative of x minus 3, which is just 1. So now we're ready to evaluate this fraction. Negative 3 times 2 times 3 ought to be negative 18 over 3 squared is 9 plus 3 is 12, and 12 squared is 144. So we have negative 18 over 144. And then we have plus 1 over 3 plus 1 is 4, and 4 squared is 16. So we got some options here on this. We do need to simplify this down a little bit. So we can certainly turn the 144. We can divide that by 16. Actually, 9 times 16 is 144. So conveniently, we could reduce that fraction down to negative 2 over 16 plus 1 over 16. Right? We don't want to take it all the way down to negative 1/8, because then we're just going to have to bring it back up to the negative 2/16. So negative 2/16 plus 1/16 is just negative 1/16. So now we're moving on to some slightly different looking limits here. Next few are going to be exponential functions, so e to the 7x minus 2 here. Now, what I like to do is I like to write out that u is equal to 7x minus 2 and just get rid of that exponent. And say as x goes to infinity, that's clearly infinity minus 2, so u is also approaching infinity. So we could rewrite this limit as a limit as u approaches infinity of e to the u. And we know that as e to the u goes to infinity, right? E to the infinity is just infinity. For our next one here, we're going to be approaching infinity for e to the negative x cubed plus x squared plus x plus 1. So I'm going to let u equal negative x cubed plus x squared plus x plus 1. And recognize that as x goes to infinity, the term that dominates this is the negative x cubed. So u is going to approach negative infinity cubed, or negative infinity. So we could rewrite this as a limit as u approaches negative infinity of e to the u. Well, that's equal to e to the negative infinity, which is 1 over e to the infinity, or 1 over infinity, which is just 0. For our next one here, we'll do the same thing. We'll let u equal x squared minus x. And as x goes to negative infinity, the x squared term dominates, and u approaches negative infinity squared, which is just infinity. So we could rewrite this as a limit as u approaches infinity of e to the u, which is, of course, e to the infinity, or just infinity. Here we'll do u equals x to the 5th plus x plus 2. As x goes to negative infinity, u is going towards negative infinity to the 5th, because that 5th power is the one that dominates. So negative infinity to the 5th power is still negative infinity. So we end up with a limit as u approaches negative infinity of e to the u, which is e to the negative infinity, which is just 0. For our next one here, we've got the limit as x approaches infinity of the natural log of 5x minus 7. So for these ones, we need to remember that the natural log function looks like this, right? As it approaches infinity, as x approaches infinity, the natural log function equals infinity. And as we approach 0 only from the right-hand side, it equals negative infinity. So here we've got u equal to 5x minus 7. Well, if x goes to infinity, u goes to 5 infinity minus 7, which is still infinity, giving us a limit as u approaches infinity of the natural log of u, which of course is the natural log infinity, which, as we just said, goes towards infinity. We'll use a similar process here. We're just going to do a limit with the u substitution. We'll let u equal 2x squared plus 8x minus 3. And as x goes to negative infinity, the x squared term, that highest power, is what dominates. So negative infinity squared is infinity. So as x goes to negative infinity, u goes to positive infinity. So this can be rewritten as a limit as u approaches positive infinity of the natural log of u, which is the natural log of infinity, which is infinite. Another similar one here. We're going to do u is equal to x cubed plus x squared plus x plus 1. As x goes to negative infinity, the x cubed term is going to dominate, and u is going to approach negative infinity cubed, which is still negative infinity. So this becomes a limit as u approaches negative infinity of the natural log of u. Well, that's the natural log of negative infinity. Well, we can't take the natural log of negative numbers. So this limit does not exist. And we should see that if we think about the graph of natural log, it never goes towards negative infinity. Like the x values never go towards negative infinity. We can't take those natural logs. So this limit doesn't exist. Here's where these natural log ones start to get a little bit trickier, where people start to have some trouble with them. So we still want to do the same thing. We want to let u equal 1 over x squared plus 1. And as x goes to infinity, right, u is going to approach 1 over infinity, right? A positive 1 over a positive infinity. So what we want to be very careful about is not to write a limit as u approaches 0 of the natural log of u. Because that limit, right, we know that as we approach 0, we can't actually do that because there's nothing coming from the left-hand side. But if we're careful about this and we recognize that it's a positive 1 over a positive infinity, we know that we can only be approaching 0 from the right-hand side because we're doing both a positive number divided by a positive number. So now this limit actually becomes the limit as u approaches 0 from the right of the natural log of u, which is negative infinity. And if you go in and just write the limit as u approaches 0 of natural log of u equals negative infinity, that's wrong, and you're not going to get all the points for that. Right? You've got the right idea, but the limit as we approach 0 of natural log doesn't exist. Only the limit as we approach 0 from the right exists. So you have to make sure that you include this plus sign here. If you don't have that, you're not going to get credit for the problem. For our next one, we're going to do the same thing. We're going to let u equal 3 over x squared plus 1. And as x approaches negative infinity, u is approaching a positive 3 divided by negative infinity squared plus 1. Well, negative infinity squared is infinite, right? We have a positive 3 and a positive infinity, which means we're approaching 0 from the right-hand side. So this is a limit as u approaches 0 from the right of the natural log of u, and as we just said, that's equal to negative infinity. All right, for our next one, we're going to do the same process. We're going to let u equal negative 3 over x cubed minus 1. Well, as x goes to infinity, u is going to a negative 3 over an infinity cubed, which is positive infinity. So now we have 0, but that 0 we're approaching from the left-hand side because it's always negative divided by always positive. So a negative divided by a positive is a negative, right? So we can only approach 0 from the left-hand side. So this becomes a limit as u approaches 0 from the left of natural log of u. Well, the natural log function looks like this. We can't approach 0 from the left-hand side. There are no values to the left of 0. So we will say this limit does not exist. And here we've got another one similar. We'll let u equal 5 over x to the 4th minus x. As x goes to negative infinity, u is going towards 5 over, the dominating term there is the x to the 4th, right? So negative infinity to the 4th is a positive infinity. So we have positive 5 over positive infinity, which is 0 from the right. This is a limit as u approaches 0 from the right of the natural log of u, which we know is equal to negative infinity. All right, now we want to find the limit as x approaches 0 of x squared times the sine of 1 over x. So this problem here is, people tend to just say, oh, this is equal to 0 because it's 0 times something. Well, the sine of infinity, right, it's 0 times something that doesn't exist. Right? We can't do 0 times a number that doesn't exist and just say it's 0. Now, it's possible that it equals 0, but it's also possible that it doesn't exist. So what we're going to do is we're going to use what we know about the sine function to use the squeeze theorem. So we know that the sine of anything is between 1 and negative 1. So I can make an inequality that says the sine of 1 over x is between negative 1 and 1. And if I multiply each piece of this by x squared, then I have the function that I'm trying to find the limit of, x squared sine of 1 over x, squeezed between two other much simpler functions. And the squeeze theorem says that if the functions are all continuous on an open interval surrounding 0, except maybe not at 0, which is good because our function is not defined at 0, then if we can find the limit as x approaches 0 of the first function, which happens to be 0, and we can find the limit as x approaches 0 of the third function, which also happens to be 0, then by the squeeze theorem, sometimes called the sandwich theorem, the limit as x approaches 0 of the function that has been squeezed between them is also equal to 0. Now this one looks like an exceptionally similar setup here. right? We have the cosine of something that's undefined, right, which is undefined, times 0. So this is another candidate for the squeeze theorem. We'll say that the cosine of 2 over x squared is also always between -1 and 1. But this time, we have to multiply by the cube root of x. And one of the issues there, well, the big issue here is that the cube root of x is sometimes positive, and it's sometimes negative, right? If x is greater than 0, then the cube root of x is greater than 0. But if x is less than 0, then the cube root of x is less than 0. And because this is an inequality, it matters if I multiply by something that's positive or something that's negative. So we'll come right back to this. In the previous problem, we were multiplying by x squared. Well, x squared is always positive, so there's no issue multiplying an inequality by something that's always positive, right? We multiplied by x squareds. But here, because we're multiplying by something that we're not sure whether it's positive or negative, we have to split it into two separate cases. So if x is greater than 0, then multiplying by the cube root of x is no problem. We can just say that this is true. But if I'm multiplying by something that's negative, then there's an issue here. I need to say that the negative cube root of x is greater than or equal to the cube root of x times the cosine of 2 over x squared, which is greater than the cube root of x. So I have to have two separate cases here. And then when I look for my different limits, we again need to be careful, because on the left side over here, where x was greater than 0, I can no longer just do a limit as x approaches 0. Since x is greater than 0, I have to approach 0 only from the right-hand side. So we'll do a limit as x approaches 0 from the right of the negative cube root of x, which is 0. And we'll also do a limit as x approaches 0 from the right of the positive cube root of x, which is also 0. Right? So that should tell us that the limit as x approaches 0 from the right of the cube root of x times the cosine of 2 over x squared should also be 0. And on this other side, we'll have to do a limit as x approaches 0 from the left, because x is less than 0. We can only approach 0 from the left-hand side. So we have the limit as x approaches 0 from the left of negative cube root of x, which is 0. And that's the same as the limit as x approaches 0 from the left of the cube root of x. Therefore, the limit as x approaches 0 from the left of the cube root of x times the cosine of 2 over x squared should also be 0. And now, because the two-sided limits, the one-sided limits are both equal to 0, that tells us that the limit as x approaches 0, the two-sided limit of our function, the cube root of x times the cosine of 2 over x squared, should also equal 0. All right, for our next one here, we've got a couple of options. One is to just factor that denominator, and the other is to recognize that this is 0 over 0 and use L'Hopital's rule. So it's just really up to you what you want to do. Both methods will work just fine. So I think we'll just factor this time. But if you want to use L'Hopital's rule, that's fine too. The limit as x approaches 4 of root x minus 2 is going to stay in the numerator, but the x minus 4 in the denominator will factor. Right? And x minus 4 is just a difference of squares, right? It's root x squared minus 2 squared. So I could write it as root x minus 2 and root x plus 2. Well, that allows me to cancel the root x minus 2's, giving me a limit as x approaches 4 of 1 over root x plus 2, which is 1 over the square root of 4, which is 2, plus 2, which gives us 1 over 4. And if you'd use L'Hopital's rule, you'd end up with the same exact thing. All right, for our next one here, we've got the limit as x approaches 7 of root x plus 2 plus x minus 10. over x squared minus 49. So we've got options here again, but I think the easiest thing to do here is going to be to use L'Hopital's rule this time. So we'll use the L'Hopital's rule for this one. The limit as x approaches 7 of root x plus 2 plus x minus 10, right? That's the square root of 9, which is 3 plus 7 is 10, minus 10 is 0, right? And the limit as x approaches 7 of x squared minus 49 is also equal to 0. Therefore, we can use L'Hopital's rule to write this as a limit as x approaches 7 of the derivative of root x plus 2, which is 1 over 2 root x plus 2, plus the derivative of x, which is 1, and then the derivative of the minus 10 is 0, all over 2x, right? The derivative of x squared minus 49. Then we can just plug in our values here. So that becomes 1 over 2 times 3, so 1/6 plus 1 over 2 times 7, which would be 14. So we have 1/6 plus 1 over 14. That'd be 7/6 over 14. Well, 7/6 over 14, we can just do the 7 over the 14 should cancel out to become a 1 over 2. So it's 1 over 6 times 2, or 1/12. For our next one here, we've got the limit as x approaches 1 of x to the 1/5 minus 1 over x minus 1, which is 0 over 0. We have two options. One option is just to use L'Hopital's rule, which now that we know L'Hopital's rule is probably a much easier option. The other is to do a u substitution for x to the 1/5. Right? So we could do that, but I think since we know that the limit, we're at the limit as x approaches 1 of x to the 1/5 minus 1 is 0, and the limit as x approaches 1 of x minus 1 is 0, we might as well just use L'Hopital's rule. Now that we have that at our disposal, we can say this is a limit as x approaches 1 of the derivative of x to the 1/5, or 1/5 of, 1/5, right? 1/5 of x to the negative 4/5, and the derivative of minus 1 is 0, over x minus 1's derivative, which is just 1. Well, then we can just plug in 1 to this, 1/5 of 1 to the negative 4/5. Well, 1 to any power is just 1, so we have 1/5 times 1, which is 1/5. All right, our next one here, we have a limit as x approaches 1 of x to the 2/3 plus x minus 2 over x squared minus 5x plus 4. If we look at what the limit as x approaches 1 of the numerator is, we can see that's 0. And if we look at the limit as x approaches 1 of the denominator, we get 1 minus 5 plus 4, which is also 0. So we'll just use L'Hopital's rule here. And if we use L'Hopital's rule, we'll take our derivative, getting the limit as x approaches 1 of 2/3 x to the negative 1/3 plus 1 all over 2x minus 5. And we can then just evaluate that when x is 1. So we have 2/3 of 1 to the negative 1/3. Well, that's just still 2/3, right? Plus 1 all over 2 times 1, which is 2, minus 5 is negative 3. So we have 2/3 plus 1, which would be 5/3, divided by negative 3, which is negative 5 over 9. All right, our next one here, we have a limit as x approaches 6 of the cube root of x plus 2 minus 2 over 2x minus 12. So we got two options here. One option is to do a u substitution for the cube root of x plus 2, but I think that's kind of overkill here, because if we do a limit as x approaches 6 of the cube root of x plus 2 minus 2, we get 0. And if we do a limit as x approaches 6 of 2x minus 12, we get 0. So we might as well just go right ahead and use L'Hopital's rule. Right? So the derivative of x plus 2 to the 1/3, sure we write that we're using L'Hopital's. Right, so we'll do the limit as x approaches 6 of the derivative of x plus 2 to the 1/3, which will be 1/3 of x plus 2 to the negative 2/3. And then the derivative of minus 2 is 0. And then in the denominator, the derivative of 2x minus 12 is just 2. So really what we've got here is a 1 in the numerator over a 3 times x plus 2 to the 2/3 times 2. And it's a limit as x approaches 6 of that. And so then we'll just plug in 6. We end up with 1 over, well, the 3 times the 2 is 6. And then 6 plus 2 is 8. So it's 8 to the 2/3. Well, the cube root of 8 is 2, and 2 squared is 4. So this is 1 over 6 times 4, or 1 over 24. All right, for this one, this one's kind of a mess. If I plug in 3, right, all those x minus 2s are just going to be 1s, and the cube roots of them will be 1s, and the squares of them will be 1s. So it looks like this is going to, I think, end up being a 0 over 0. So let's see what the limit as x approaches 3 of the numerator is. Well, actually, let's not bother with writing it out, because I don't think we want to use L'Hopital's rule for this. So if we plug in 3, we're going to get 1 minus 5 plus 4, which is definitely 0. And we're going to get 1 minus 3 plus 2, which is also 0. So for this one, we're not going to use L'Hopital's rule, because that's just, I don't know, it seems like it's a mess. So what we'll do is we'll let u equal the cube root of x minus 2. Right? Well, if u is the cube root of x minus 2, and x is approaching 3, then u is approaching the cube root of 3 minus 2, which is just 1. So we can rewrite this as a limit as u approaches 1 of u squared minus 5u plus 4 over u squared minus 3u plus 2. And now from there, we have two options. We can either use L'Hopital's rule, because that's still 0 over 0, or we can just factor. I think factoring is a little bit quicker than writing out all the L'Hopital's rule stuff. We have u minus 4 and u minus 1, and then we have u minus 2 and u minus 1. And those u minus 1s will just cancel. We get a limit as u approaches 1 of u minus 4 over u minus 2, which we can then just plug in 1. We get negative 3 over negative 1, which is just 3. All right, for our next one here, if we try to look at this one here, when we plug in 5 to the numerator, we're clearly going to get 0. And when we plug in 5 to the denominator, it sure looks like we're going to get 0 also. So the limit as x approaches 5 of 5 sine pi x plus x minus 5. Well, the plus x minus 5 part's just 0. Then we have 5 sine of 5 pi, and the sine of 5 pi is also 0, so that's just 0, which means this is another good one for us to use L'Hopital's rule on. So using L'Hopital's rule, we're going to have a limit as x approaches 5 of the derivative of x cubed minus 125, which will be 3x squared, and then the derivative of 5 sine pi x, which will be 5, times the derivative of sine pi x, which will be pi cosine pi x, and then plus 1. And that minus 5 goes away. So if we plug in 5 here, we're going to get 3 times 25, which is 75, divided by 5 pi times the cosine of 5 pi plus 1. Well, the cosine of 5 pi, right, that's just, it's the same thing as pi, right, because every 2 pi it rotates, right, it goes around, right? So it's really just like the cosine of pi, and the cosine of pi is negative 1. So we end up with 75 over negative 5 pi plus 1. And for our next one here, this one, we could try to use L'Hopital's rule on this, but that seems like it's going to be kind of messy. So we want to think back to what we did in the limits unit, which is take out the 1/2, like that 2 in the denominator, and write this as the limit as x approaches 0 of, well, that numerator sure seems like it has coefficients of 1, 3, 3, and 1 with alternating signs. And that looks like the third row of Pascal's triangle. Right? So that numerator actually is going to factor into 1 minus cosine of x to the third. And so now, because both the numerator and the denominator are being raised to the third power, we can write this as 1/2 the limit as x approaches 0 of 1 minus cosine x over x all to the third. And because we know that the limit as x approaches 0 of 1 minus cosine x over x is 0, this is just 1/2 times 0 to the third, or 1/2 times 0, which is just equal to 0. So now we're going to look at finding some limits just based on a graph. So the first limit we're asked to find is the limit as x approaches -6 from the left. Well, here's -6 right here, right? And if we're going to approach this from the left-hand side, we'd have to have function over here, which we don't. So that limit doesn't exist. If we want to approach -6 from the right, we don't have to worry about what's going on the left-hand side. We're going towards a y value of 4. But we can't have an actual limit as x approaches -6, because in order for the two-sided limit to exist, both the left and the right limits have to equal each other, which they don't. As x approaches -5, from both sides, we're just going towards that point at y equals 2. So that limit should just be 2. As we approach -4, the two-sided limit, we're going down towards 0 from both sides. So that limit should be 0. As we approach -2 from the left, we're going towards 2, right? So that should be 2. As we're going towards -2 from the right, we're also going towards y equals 2. And the two-sided limit should also be 2, because if and only if the left and the right limits are equal to each other, does the two-sided limit exist? And then it is the same. We don't worry about this point up here. That point up there has nothing to do with the limit. It only has to do with what we're approaching as we get close to that x value. As we approach 0 from the left, we're going towards, looks like the origin, so that'd be a y value of 0. But as we approach 0 from the right, we're going down towards this open point here, which is at y equals -2. And because the limit from the left was 0 and the limit from the right was -2, the limit as we approach 0, the two-sided limit, does not exist. As we approach 1, we're just going up from both sides to this point at y equals 1. So the limit as x approaches 1 is 1. As we're approaching 2 from the left, we're going up towards that point at y equals 4. But as we approach 2 from the right, we're going up to a y value that's getting very, very close to 2. Since those two limits aren't the same, the two-sided limit at 2 does not exist. As we approach 3, we're just going towards this value at 1. As we go towards 4, we're just going towards this value where y is equal to 0. As we approach 5, we're just going right here towards this value where y is equal to -1. And as we approach 6 from the left, we're going down towards this value here at -2. But we can't approach 6 from the right because there is no function to the right of +6. I guess at -6, but we can't approach 6 from the right-hand side because there's no function to the right of 6. And so that means that the two-sided limit also does not exist. So we'll work through another one of these with a graph here, and then we'll just move on to some other types of questions. So as we approach -6 from the left, once again, there's nothing to the left of -6, so that does not exist. But as we approach -6 from the right, we're going down towards that y value of -4. But since the two limits, the left and the right, aren't the same, the two-sided limit does not exist. As we go towards -5, we're going towards this y value of 1. So that one will be 1. As we go towards -4, the two-sided limit, right? Well, towards -4 here, we're going towards 4 from both sides for the y value. So that one will be 4. As we approach -3 from the left, now we're going up to this open circle up there, which is at 5. And as we approach -3 from the right, we have this linear piece that's also going towards that value at 5. Meaning that the limit as x approaches -3 of f of x, the two-sided limit, is also 5. Just like in the last problem, we don't worry about this stray point that's just kind of hanging around there. We're not approaching that value. That's just the value we happen to be at when x equals -3. Our next one is what happens as we approach -1 from the left. So we're going down to this open circle, which is at 3. As we approach -1 from the right, though, we're going down to this closed point at y equals 0. So that one will be 0. And since the left and the right-hand limits aren't the same, the two-sided limit does not exist. As x approaches 1, we're just going towards x equals 1 from both sides. The y value is 2 there that they're both approaching. As we approach 2 from the left-hand side, we're going towards a y value of 3. We don't ever get there because of the open circle, but that's what we're approaching. And as we approach 2 from the right-hand side, we're going down there towards a y value of 2, which again, we don't hit because of the open circle, but we're still approaching it. The two-sided limit, as x approaches 2, then does not exist because the left and the right limits didn't match up. One was 3 and the other was 2. The limit as x approaches 3 is just from both sides there approaching a y value of 3 as well. And as x approaches 4 from both sides, the y value is also approaching 4. Then as x approaches 5 from both sides, right? We look from the left and from the right, both sides we're approaching 4. And just because there's an open circle there doesn't mean that that limit doesn't exist. As we approach 6 from the left, we're going back to, that y value there at 5 was 3, not 4. Just misreading my graph here. That's 3 here. So the limit as x approaches 5 of f of x is 3. Okay. And so now our limit as we approach 6 from the left-hand side, we're going up towards 4. But there's no way for us to approach 6 from the right-hand side because there's no function to the right, so that limit does not exist. And then lastly, the limit as x approaches 6 doesn't exist because the one-sided limits weren't equal to each other. For our next problem here, we're going to use the intermediate value theorem to determine if there's a solution to x cubed plus 2 equals 0 on the interval -2 to -1. So we'll start off by stating that our function, right, f of x, which is x cubed plus 2, is continuous on the interval from -2 to -1 because it's a polynomial. Right? And the fact that it's a polynomial is always an acceptable reason to state something's continuous, also to state that it's differentiable, but we don't need that for our limits and continuity stuff. So then we'll just say f of -2, we'll find f of -2. So f of -2 is -2 cubed, which is -8 plus the 2 is -6, noting that that's negative. And we'll look for f of -1, which is -1 cubed, which is -1 plus 2, which is +1, which we'll note is greater than 0. And so because there is a sign change there, we can say, right, by the intermediate value theorem, yes, f of x does equal 0 on the interval from -2 to -1 because of this sign change right here. And you need to indicate that there was a sign change there, either in words down here or by stating that one was positive and one was negative. All right, for our next one, we've got x squared minus cosine x. We want to show it has an x-intercept on the interval 0 to pi. So first, we'll state that this function is continuous. Right? We'll say f of x is continuous on 0 to pi Because it's just a difference of continuous functions, right? X squared is continuous, it's polynomial, and the cosine function is continuous because it's a sinusoidal function. Sinusoidal functions are continuous for all real numbers. So then we want to show that f of 0 is either positive or negative, and f of pi is the opposite. So f of 0 is 0 minus the cosine of 0, which would be -1. That's clearly negative. And f of pi is pi squared minus the cosine of pi. Now, it doesn't really matter exactly what the cosine of pi is, even though, we should know, right, that the cosine of pi is -1. So that becomes pi squared plus 1, which is greater than 0. It didn't really matter what the cosine of pi was, though, because we knew it was between -1 and 1, and pi squared is much more than that. So if we subtract anything between -1 and 1, we're going to clearly get a positive number still. So because of this sign change and that it's a continuous function, yes, IVT says that f of x has an x-intercept, right, on the interval 0 to pi, right? And we always do this open interval here because that's what the result of the intermediate value theorem says. But also, we see that the x-intercept is not at 0 or at pi, so it's clearly on the interior of that portion. All right. All right, for our next one here, we're going to do the same process. F of x has a discontinuity at x equals -1. But that's not on our interval from 1 to 3. So f of x is continuous on 1 to 3 because rational functions are continuous on their domains. And we can clearly see that the only domain restriction is x cannot be -1. So now we'll just find f of 1. F of 1 is 1 minus 2, which is -1, over 1 plus 1, which is 2. That's clearly negative. And f of 3 is 1 over 4, which is clearly positive. So yes, f of x equals 0 on 1 to 3 by the intermediate value theorem. All right, another one here. We have 3 plus ln x equals x cubed. So what we want to do is we want to rewrite this as 3 plus ln x minus x cubed equals 0, and show that this function has an x-intercept, or a solution. This equation has a solution on the interval between 1 and e. So this is continuous, or we'll call this f of x. F of x is continuous on 0 to infinity, right, which is its domain. So it must be continuous on 1 to e, because 1 to e is a subset of 0 to infinity. Then we'll find f of 1. F of 1 is 3 plus the natural log of 1, which is 0. So 3 plus 0 minus 1 cubed, which is 2. So clearly a positive number, right? And then we also have an f of e, right? So f of e is going to give us 3 plus the natural log of e, which is 1, minus e cubed. Well, that's 4 minus e cubed. Well, we know that e is more than 2, and 2 cubed is already 8, so that's clearly going to be a negative number. And so f of x equals 0, on the interval 1 to e by the intermediate value theorem, which indicates that 3 plus ln x equals x cubed on the interval from 1 to e. All right, we got one more of these, I think. So we want to show that there's a solution to root x plus 2 equals 2x squared plus 1 between -1 and 0. So we'll start off by just saying that we're going to turn this function into a slightly different function. We're just going to make it f of x equal to 2x squared plus 1 minus root x plus 2 and show that that equals 0. And if we can show that that equals 0, then clearly the thing above must be true. And so this is continuous on its domain. Its domain is -2 to infinity. And since -1 to 0 is on -2 to infinity, we can say that f of x is continuous on -1 to 0, which is a subset of its domain of -2 to infinity. Then we'll just evaluate f of -1. Well, f of -1 is 2 times -1 squared is 2, plus 1, which is 3, and then minus 1, which is just 2, so that's positive. And then f of 0 is going to equal 0 plus 1 minus the square root of 2. Well, the square root of 2 is more than 1, so 1 minus root 2 is negative. So by the IDT, f of x equals 0 on the interval -1 to 0, and root x plus 2 equals 2x squared plus 1, somewhere on the interval from -1 to 0 as well. So our next little set of problems here, we're going to be finding the discontinuities and classifying them using limits. So we'll start off by just factoring the denominator here to see when this has discontinuities, right? So x plus 5 and x plus 3. So we know this has discontinuities at x equals -5 and x equals -3. So we'll need to do the limits at both of those values. So the limit as x approaches -5 of f of x, well, we can cancel the x plus 5s. This is just the limit as x approaches -5 of 1 over x plus 3, which happens to be -1/2. But we know that f of -5 does not exist. So if the limit exists, but the function doesn't exist, that tells us that we have a removable discontinuity at that point. And then we'll do the limit as x approaches -3 of f of x. Well, the x plus 5s, we can still cancel them if we want, right? Or we don't have to also, it doesn't really matter. So if we don't cancel them, it's -3 plus 5, which is 2 over 2 times 0. Well, 2 over 0 is either positive or negative infinity. So if the limit is infinity, that tells us that it's an infinite discontinuity. All right, here we just have 2 over x minus 1. That's a pretty straightforward one. It's just going to have a discontinuity at x equals 1, right? X can't be 1. So we just do the limit as x approaches 1 of 2 over x minus 1 and see that it's 2 over 0. Well, since it's 2 over 0, we know that's either positive or negative infinity, and x equals 1 gives us an infinite discontinuity. For our next one, we need to factor that denominator. So we're going to have x minus 1 in the numerator, but in the denominator, we're going to have an x times some other stuff. Right? This is x times x squared minus 2x plus 1. So really, that's just x minus 1 squared there in our denominator. So kind of was a little premature there. We'll just have x minus 1 squared. And so our only discontinuities are at x equals 0 and x equals 1. So we'll start with 0. We'll do the limit as x approaches 0 of f of x. right? Which is just going to give us 0 minus 1 is negative 1 over 0 in the denominator, right? So negative 1 over 0 we know is positive or negative infinity. So x equals 0 is an infinite discontinuity. And when we do x equals 1, a limit as x approaches 1 of f of x, we can cancel out one of these x minus 1s in the denominator with the 1 in the numerator, and we get 1 over x times x minus 1. So usually we think removable discontinuity when we do that. But here, when we plug in 1, we still get 1 over 0, which is positive or negative infinity. And because of that multiplicity of 2 on that root, we ended up with x equals 1 also being an infinite discontinuity. So something to be watching out for. And the reason why we actually do the limits rather than just seeing if a term cancels. All right, our next one here, we're going to look at our denominator. Right, our denominator is going to be undefined when x is 0 and x is negative 2. So we need to do the limits at both of those. So we'll first do the limit as x approaches 0 of f of x. And note that that's 0 over 0. So what we want to do is we want to separate out the piece of it that, that we know can sort of go together. And that's the sine of 3x over the x. Right? And if I put the limit as x approaches 0 of x minus 1 over x plus 2 there next to it, now I should be able to evaluate both of these limits. And the sine 3x over x1, we can throw a 3 in the denominator and the numerator and then pull that 3 out to the front. So this becomes 3 times the limit as x approaches 0 of sine 3x over 3x. And then times, well, that one we can just evaluate. It's negative 1 over 2. So what we end up with is 3 times 1, because the limit as x approaches 0 of sine 3x over 3x is 1, and then times negative 1/2. So we end up with a limit of negative 3/2. But of course, we know that the function doesn't exist at 0. Right? F of 0 does not exist, and therefore, this should be a removable discontinuity at 0. And then when we go down and do negative 2, well, the limit as x approaches negative 2 of f of x, well, in the numerator we have negative 3 times the sine of negative 6. Those are all just numbers. Divided by negative 2 times 0. Well, a number divided by very close to 0 is positive or negative infinity, which tells us that x equals negative 2 is an infinite discontinuity. All right, for our next one here, the first thing we want to check is if there are any discontinuities of each of the pieces of this function on the pieces of their domain. So x plus 2 is always continuous. X squared plus 2 is always continuous. But 6 over 3 minus x is not always continuous. It's got a discontinuity at x equals 3, which is part of x is greater than 2. So we'll start off by doing the limit as x approaches 3 of f of x, which is 6 over 0, or positive or negative infinity. So x equals 3 is going to be an infinite discontinuity. Then we have to check what's going on at negative 1, where the two pieces of this meet up. So we'll do a limit as x approaches negative 1 from the left of f of x. So that'll be negative 1 plus 2, or 1. And we'll also do a limit as x approaches negative 1 from the right of f of x, which will be negative 1 squared plus 2, which equals 3. Well, since the limit as x approaches 1 from the left, 1, does not equal the limit as x approaches negative 1 from the right, 3, then we will say there is a jump discontinuity at negative 1. And lastly, we'll look at 2. And as we look at 2, we're going to be extra careful about that, right? Because we see that neither the x greater than 2 or the x less than 2 have an or equal to. So there's definitely a discontinuity there. It's either going to be removable if the limits from the left and the right are equal, or it's going to be jump if they are not. So let's check those limits. The limit as x approaches 2 from the left of f of x is 2 squared plus 2, which is 6. And the limit as x approaches 2 from the right of f of x is 6 over 3 minus 1, which is also 6. So since those match up, if the function was defined there, we wouldn't have a discontinuity. But f of 2 does not exist, which tells us the limit exists, but the function doesn't. X equals 2 is a removable discontinuity. So always make sure you check those inequalities in these piecewise defined functions. All right, for our next one here, we look at each of the pieces, going from the bottom up because that's the easiest. 5x minus 2, that doesn't have any discontinuities, nor does x cubed plus 1, but the natural log of negative x does. We can only take the natural log of positive numbers, which means that I can take the natural log of negative x only when x is negative, right? Well, x is less than or equal to negative 1 isn't going to give me any extra discontinuities there for that, right? Because that would be continuous on negative infinity to 0, which negative infinity to negative 1 is part of that. So now we just need to do the limits as we approach negative 1 from the left and from the right, as well as for 2. So as we approach negative 1 from the left here, we just end up with the natural log of the negative 1, which is natural log of 1, or 0. And as we do the limit as x approaches negative 1 from the right of f of x, negative 1 cubed is negative 1 plus 1 is 0. So those match up, which means we do not have a discontinuity at x equals negative 1 because the function is defined at negative 1. We have a less than or equal to there. Then we'll do the limit as x approaches 2 from the left of f of x, which will be 2 cubed plus 1, which is 9. And we'll do the limit as x approaches 2 from the right of f of x, which is 5 times 2, 10, minus 2, which is 8. Well, since the limit as x approaches 2 from the left does not equal the limit as x approaches 2 from the right, x equals 2 is a jump discontinuity. All right, we've got another one of these here. We've got x over 6. That's continuous for all real numbers. We've got x squared minus 8, which is continuous for all real numbers. And we've got 1 over x minus 1, which has a discontinuity at x equals 1, which unfortunately x equals 1 is between negative 2 and 3. So we'll start off with a limit as x approaches 1 of f of x, which is 1 over 0, which is, of course, positive or negative infinity, which tells us that x equals 1 is an infinite discontinuity. Then we'll look at the pieces at negative 2 and at 3. We're not guaranteed discontinuities at either of them because there is an or equal to for both of them, but we still need to check this. Right? So if the limits are the same from the left and the right, there won't be a discontinuity, but if they're different, it'll be a jump discontinuity. So the limit as x approaches negative 2 from the left of f of x, we'll plug that into x over 6, so that's negative 2/6, or negative 1/3. And the limit as x approaches negative 2 from the right of f of x is 1 over negative 2 minus 1, which is also negative 1/3. So therefore, we do not have a discontinuity at negative 2. Then we need to check at 3. The limit as x approaches 3 from the left of f of x is 1 over 3 minus 1, which is a half. And the limit as x approaches 3 from the right of f of x is 3 squared minus 8, which is 1. Well, that means that 1/2 does not equal 1. The limit as x approaches 3 from the left of f of x does not equal the limit as x approaches 3 from the right of f of x. Therefore, x equals 3 is a jump discontinuity. All right, we're going to do a couple here where we find a value of a so that our function is continuous for all real numbers. So we can see that x squared minus 7x plus 12 over x minus 3 is continuous for all real numbers, except 3. Luckily, that's when our function doesn't equal x squared minus 7x plus 12 over x minus 3. Right? At x equals 3, it's ax plus 2. So the definition of continuity says that the limit as x approaches 3 of f of x needs to equal f of 3. Well, we can find this limit by just factoring this out, right? The limit as x approaches 3 of x minus 3 times x minus 4 over x minus 3. And that needs to equal f of 3. Well, f of 3 is just 3a plus 2. When we cancel these x minus 3's, we can then evaluate the limit as x approaches 3, right? We just end up getting 3 minus 4, which is negative 1, equals 3a plus 2. We get negative 3 equals 3a, or a is equal to negative 1. For our next one, same idea here. We're just going to look for the limit as x approaches 0 of f of x, which means we're going to factor out the x from the numerator, giving us x times x minus 6 over 2x. Cancel out the x's, giving us x minus 6 over 2, and then evaluate that at 0, which gives us negative 6 over 2, or negative 3. We'll just set negative 3 equal to f of 0, right? So negative 3 is equal to negative 6a. And if we divide by negative 6, we get a equals positive 1/2. All right, we got another one of these here. I think this is the last one like this. We'll do the limit as x approaches 0 of f of x. And in order to do that, we're going to recognize that that's 0 over 0, right? So we'll say that the limit as x approaches 0 of x cubed minus x squared is 0, and the limit as x approaches 0 of 1 minus cosine x is equal to 0. So using L'Hopital's rule, we can say this is the limit as x approaches 0 of, we'll just do 3x squared minus 2x over the derivative of 1 is 0, and the derivative of negative cosine is positive sine of x. Well, once again, I think we can see now, again, that the limit as x approaches 0 of 3x squared minus 2x is 0, and the limit as x approaches 0 of sine x is 0. So using L'Hopital's rule again, we'll get the limit as x approaches 0 of 6x minus 2 over the cosine of x, which will just be negative 2 over the cosine of 0, which is 1, or negative 2. So our limit is equal to negative 2. We just need to set that equal to f of 0. So we have negative 2 is equal to negative 6a. Right? If x is 0, we have 2a times negative 3. And so if we divide by negative 6, we get a is equal to 2/6, which is 1/3. All right, and we've got just a couple more here to go. We're going to try to find values of a and b so that the function here is continuous for all real numbers. So we'll start off, we're going to start off here by doing the limit as x approaches negative 2 from the left of f of x, which is negative 2 plus 2, or 0, and the limit as x approaches negative 2 from the right of f of x, right, which will be, well, if we plug in negative 2 for x, we get 4a minus 2b. So in order for this function to be continuous at negative 2, we need 4a minus 2b to equal 0. Then we'll do a limit as x approaches 3 from the left of f of x, right? Which will be, well, in this case, we've got 9a plus 3b. And we'll do a limit as x approaches 3 from the right of f of x, which will be 3 squared minus 8, or 1. So what we need is, we need 9a plus 3b to equal 1. So we've now got a system of equations here that we want to solve, right? 4a minus 2b equals 0, and 9a plus 3b equals 1. Well, this one tells us that 2b equals 4a, or b is equal to 2a. So I can use substitution, plug b equals 2a in right here to get 9a plus 3 times 2a, which would be 6a, equals 1. Or 15a equals 1, or a is equal to 1/15. Well, if a is 1/15, when I plug that back in up here, we'll just get b is equal to 2/15, right? Because it's twice of what a is. So we have a is 1/15 and b is 2/15. All right, our next one here, same basic idea. We're just going to do the limit as we approach -2 from the left and the right, and 1 from the left and the right. So we start with the limit as x approaches -2 from the left of f of x. Well, that'll be 3 times -2, which is -6 minus 4, or -10. Right? And then we'll do the limit as x approaches -2 from the right of f of x, which will be, we square -2, that's 4, and 4 times 2a is 8a. And then -2 times 3b will be minus 6b. So our first equation, and I'm going to write them up here this time, our first equation is going to be 8a minus 6b is equal to -10. Then we'll do the limits as x approaches 1 from the left of f of x, which will be 2a plus 3b. And we'll do the limit as x approaches 1 from the right of f of x, which will be 3 times 1 squared, or 3, minus 8, which is -5. Okay? So we end up with 2a plus 3b equals -5 for this one. And so what we'll want to do here is we'll just need to try to find a way to make these match up. I'm going to use a combination this time. So I'm going to keep 8a minus 6b equals -10. But if I multiply the second equation all by 2, we're going to get 4a plus 6b is equal to -10. And now I can add these together. Right? 8a plus 4a is 12a. -6b plus 6b is 0. And -10 plus -10 is -20. So a is equal to -20 over 12, or a should be equal to -5/3. Well, if a is -5/3, we can plug that back in and say 2 times -5/3 plus 3b is equal to -5. So we have -10/3 plus 3b equals -5. Well, -5 is -15/3. So we have 3b equals -15/3 plus 10/3, which would be -5/3, or b is equal to -5/9. And we just got 2 more here to go, and we'll be finished with this assignment. So we'll do a limit as x approaches -2 from the left of f of x, which will be, in this case, 3x minus 4b, right? So we've got 3 times -2 is -6 minus 4b. I should probably write the 4 minus 4b, right? And then we've also got a limit as x approaches -2 from the right of f of x, which that's going to end up being we'll square the negative 2 is 4, so 8a, and then minus 2b. So really what we need is 8a minus 2b to equal negative 6 minus 4b. Well, if we put that up here, we can add the 4b to the left-hand side there, and we get 8a plus 2b is equal to negative 6. We could also simplify that down. In fact, we probably should. Might as well simplify that down here into 4a plus b equals negative 3. Make it even easier for ourselves. Then we'll go ahead and we will do the limit as x approaches 1 for these. So we have the limit as x approaches 1 from the left of f of x. That's going to be 2a plus b. And the limit as x approaches 1 from the right of f of x, which that will just be a plus 1. So what we need is 2a plus b to equal a plus 1. Or in other words, we need a plus b to equal 1. So those are our two equations that we want to deal with. Well, I don't really need to do anything with them. If I just put this first one we found, 4a plus b equals negative 3, right below here, right below a plus b equals 1, and then subtract the two equations, I get a minus 4a, which is negative 3a. I get b minus b, which is 0, and I get 1 minus negative 3, which is 4. So we end up with a is equal to negative 4/3. If a is negative 4/3, well, we know that a plus b needs to be 1. That tells me that b is 1 plus 4/3, and 1 plus 4/3 is 7/3. And here is our very last one. So we'll do a limit as x approaches negative 2 from the left of f of x. So 3x squared at negative 2 will just be 12. So we'll have 12 plus b. And then we'll have a limit as x approaches negative 2 from the right of f of x. Negative 2 squared is 4. So 4 times the 2a is going to be 8a. And then minus 2b. And we want that to equal the 12 plus b. So if 4a, oops, not 4a, 8a. So if 8a minus 2b equals 12 plus b, then that would mean that 8a minus 3b needs to equal 12. So we'll put that up here. 8a minus 3b equals 12. Then we'll do the work for 1. We have a limit as x approaches 1 from the left. Now that's going to be 2a plus b when we plug that into the middle piece. And we'll do the limit as x approaches 1 from the right of f of x, which is going to be 3 times a times 1, so just 3a, plus the natural log of 1. Well, the natural log of 1 is just 0. So we end up needing 2a plus b to equal 3a, right? Or in other words, we just want, looks like a to equal b, right? So if a is equal to b, we can just substitute that in, right? Right here, we'll have 8a minus 3a is equal to 12, or 5a is equal to 12. So a will be 12 fifths. Well, if a is 12 fifths and a equals b, then b must also be 12 fifths. And that is the end of this homework assignment. So that's the end of our limits and continuity extra review walkthrough for our midterm. Again, use all of these midterm review assignments. Don't just look at one or two of them. Do all of these midterm reviews. So that is the end of this one.